this can be done, okay? And if it can be done, we'll do something like that. That's my intention. So where are we? Back to we started classification, so we're going to do more of that. Let's do a 5 minutes recap of what we had so far. So I did talk about decision trees. One thing that I didn't say on decision trees, perhaps it's worth saying, was a decision tree around here. We have all data, right? And all data goes into a split. What's a split? Every node that I'm splitting a decision tree. Typically in the decision tree, I have to pick a feature of the data. And sometimes I also have to pick a threshold, right? A feature that's categorical, say color. Do I need a threshold for it? No. If it's a feature is color, I could say is the feature red, and then I'll have how many branches? 2 branches, right? What if I say another split feature color? Then I'll have, how many are there? Red, blue, green, black. What if I say age? Age is numerical, right? This doesn't really worth branching, right? There's be too many branches. Right? Age could be, unless I have only 3 ages or something, right? There'll be too many branches. So what do? If I just say age, I bucket it, maybe, right? So if I say age, I could say, okay, everybody between 2 years and 6 years, between 6 and 12, between 12 and 25, and bigger than 25. I have 4 buckets for the age. What if I say, what's the other option for numerical? So I'll do another one, which is salary. I could bucket, or I could say, is it bigger than a threshold? And in which case, I have how many branches? 2 branches, yes? This threshold has to be found, right? The other ones, it's like the same is here. How do I know how to pick red? It's one of the values of the features, right? So when I say look for all the features, every one of these things is a brute force. Try all features, pick the one that's best. When we do that, sometimes we also look for the best threshold. So in here, we look for all features versus all thresholds. This could be an intensive operation. If I look at my data and I say try all features times all thresholds, it could take a while to figure out the best one. So people have thought really hard how to do this. For example, if my features are words, I'm only going to look for the thresholds based on documents that contain that word, right? It doesn't make sense to sometimes for words it's even binary. Sometimes for words people give up on a threshold. They just say, is it bigger than 0, meaning is the word in that document or not. Sometimes there is a bucketing of features that's done in advance. Every feature has a range, right? in the data from min to max. What people do sometimes to not search for threshold exhaustively, they split, they bucket the features, they do a pre-processing in advance to know for this feature salary, what data points fit in here, fit in here, fit in here, and then when I try a threshold, I use a lookup table to look up data points in here. Because otherwise, this is kind of could be an involved search, especially for a feature like salary that could have a lot of values, right? If I have a million people and everybody has different salaries, and now I pick that feature and try all possible thresholds between salaries, that could take a while. Right? But what I didn't say last time is that depending how you design the feature, sometimes it's not enough to find the feature, you have to find a way to branch it out, which may mean find the threshold. Or find some buckets. Okay? That's all I have to say about decision trees. What we want to do now is to quickly look again at regression. So what's the plan with regression? We want h of x. X is x1, x2, up to xd, right? It's a d-dimensional data point. And y is the label, xi. And yi is the label. We want h of x to be the sum of a bunch of coefficients, k, xk, regressor. This is a linear function, right? It's a linear combination of the features. We want this to be approximatively y. That's the point of regression. And people have drawn this table to say if this is x, this is y, if you get a bunch of points, you drew the best line you can between them. That would be my line h. That maps the x's into y. X in here, it's conceptual. In practice, it's a multi-dimensional x, right? This could be 54 dimension if I have span base. It could be 100,000 dimensions if I have continuous groups. That's what I want with a regression. So what is this? We call this loss or objective. How do we measure the fact that the regressor is close to the labels? We do sum for all data points, right? Between h of x I minus yi squared, sum of square loss, which is the sum of, for all data points, this is the sum over the dimensions of wk, xi, k, that's the regressor function, minus yi, that's the label, squared. We all remember this from last time? That's how we set up a regression. This mathematical function has profound implications in data science. It's used for a lot of things. Variance, k-means, regressor, all kinds of things related to this function. It's nice that it's a convex objective. And we want, of course, to minimize it, right? Because we want the smallest sum of differences. Those differences correspond to where is really the y versus where it's h of x. This is x, right? This is h of x, and this is y. And it takes this difference here, squared. Right? This sum of differences squared. The points that are close to the line have 0. The points that are far away from the line has a different square. Okay? That's what we said. And there is a solution that's theoretical. That's called the exact solution, analytical, which is the normal equations, or regression's normal equations, that tells me exactly how to solve this. I don't have it here, but maybe you guys can look at your notes. I think it says the vector W of coefficients was it x transpose x minus 1 times x times y, something like this? Anybody can look that up.
S transpose Y.
Y here?
No, S transpose Y.
Here, all right. So it says that if you think of X as a big matrix, X is a matrix of N by D, right? And you can do this operation. Theoretically, you get the best coefficient vector W's for regression. The reason I say this is theoretical, I mean no practical. While this is an exact solution mathematically, it's hard to get that in practice working. This matrix will be too big. Linear algebra operations are too unstable to perform on large data sets. Not to mention we may have noise in the Y, so if Y is not exact, we don't talk about this, but in the machine learning class we do. Noise can screw things up really bad here. We may have missing values. Nobody will do this unless there's a toy exercise when we have like 20 dimensions and so many data points. In practice, we will do that. So what do we do in practice? We do numerical optimization. That is, for example, gradient descent. That's the one we talked about last time. But there's other things that people do. Newton optimization method, coordinate descent, variational inference, and some other mathematical methods that says, I'm not going to solve it exact. I'm going to try to find the derivative. Let's call this objective J. Derivative of J with respect to some coefficient. Is, so I'm taking the differential of the objective. With my variable, which is the W, those coefficients I want to find. And then if I use gradient descent, is a iteration iterative procedure to update W towards. So the gradient descent rule was saying take the original W, the new one, and take the old one here. So how many coefficients I have? I have D coefficients. You can update all of them this way. This is what we've done last time with an example. We say if you start with some guess, and if you continue doing gradient descent on those guesses, eventually it gets to the optimal. How do we know we got to the optimal? When we are at the optimal, the derivative will be 0, right? And then this update will do what? If the differential is 0, suppose I got my W to be optimal, it will not do anything. This update will just keep the same W, right? And what is this? This is a learning rate. It's a fancy name. It determines how much you want to update, right? A big learning rate pushes the update a lot. A small learning rate does it little by little. Now, what we want to do in practice sometimes is to modify the learning rate, because the closer we are to the actual spot we want to be, the optimum W, we want to move little, but if we are far away, we want to move a lot. The gradient themselves might move a lot or little, right? Because if you think of a typical function, if you are close, this is the optimum, right, the minimum. If I'm far away, the differential is big, but if I'm close to the optimum, the differential is small. So this value alone can be big or small depending on how far I'm from the optimal. This holds for convex functions. But for non-convex functions, there is no guarantee that the differential is small, close to, right? If my function is something like this, differential could be all over the place at all times. But this objective is convex, so we don't have that issue, right? Once we descend, when we get, there's only one optimum, we descend towards it, it's good. I think this is, for now, you can set it, I don't know if the package that you use probably asks you for the learning rate as input, is that correct? If you use, anybody use linear or something to run regression? Not yet? Homework 3A?
Yeah.
They do it by themselves? It's all, okay. So sometimes it could be automatic, maybe. Sometimes it's an input parameter. This package, linear for regression, it's extremely popular. So that'd be the one I would use first. I think it's called from a lot of languages. But MATLAB implements regression too, for example. So the plan is to run this procedure. So what this is actually going to do, what is the derivative here? The derivative that I've got is h of x minus y. So this is with respect to one data point times xk. So why do I get this differential? What happens when I differentiate this function? I need a 1/2 in front of it maybe, or I put a 2 here. The 2 comes from the square, right? And then if I differentiate this remains h of x minus y, but then I have to differentiate the differential of this with respect to wk, that's going to be just xk. So I get this function here. My notation is to put the dimension indices up and the data points indices down. So my update rule would be wk is wk. This is for one data point. So this I'm going to have to sum it up. This is K. The gradient descent update over all the data points for that coefficient. And sometimes in vectorial format, I can update all the W's at once if I write it as a vector. So it's sum it up over all updates for data points for that coefficient. Now, sometimes this is done in a batch or in a 1-by-1 stochastic. So I can do it for one data point, update. This is the old one, and this is the new one. So I could pick the old one, update for one data point. Then I have a new one, new W, update for another data point, so on and so forth. That's called stochastic. If I keep an old one fixed here, and I do the sum of the updates for, say, some data points or all data points, that's called a batch update. Because I'm using the same old W to start the update for everybody. I'm not updating for each data point. I'm updating. This is equivalent to doing the update from W old 1-by-1, right? Because it's just summing up these differences here. But at all times, I'm not updating between the data points. Right? Yes?
So if you're updating at once for all the data points, what is the significance of lambda?
Lambda is still the learning rate. That tells me how much do I want to count for the differential. think about it as fixed, as a constant fix. Let's say lambda is 0.25. Okay. So it is true that modern regression change lambdas as you move along. We'll not discuss that now. Let's assume a fixed lambda that's a constant. Or you can, even better, for conceptual purposes, remove lambda altogether, right? What I'm saying is I could update one data point and then change the W, so the next one will have the updated W, or can I use the same old W for everybody to do a batch update? Stochastic update will be faster because it updates much more often, right? But it's more dangerous, it's more unsafe. The batch update is more robust, it's more safe, but it will take more time to converge to W's. So for simple data sets like spam base, if you do a stochastic update, you converge much faster because every point is pushing the W's. This new point x2 will already start from the update of the x1, so it doesn't have to push. If many points push the same way, they stack on top of each other. Okay, so let's finish regression. Also, in practice, gradient descent is not what's being used. This is for pedagogical purposes. By now, any modern system uses a much more fancier numerical optimization technique. If you want to be a data scientist, you should, at the minimum, learn the Newton's method, which is not difficult. It's just two differentials here. Newton's method, right? Sorry. Here. Newton's method. Two equations. But we won't have time to do that now. It's just Newton's method is the minimum acceptable in a production environment. It's still not a good optimization method, but anything lower than that is not acceptable.
I just wanted to ask if you make a W stochastic manner, would that change the result if you remove that muted manner?
It will not change result if the objective is convex and it's easy to converge to it. It will just make it faster. So the number of iterations, this gradient descent, like other methods, will run iteration by iteration, right? You have to run in quite a few iterations, just like with EM. Stochastic updates will converge faster to the optimal W. In particular for this objective, being convex, there is a global optimum. So all methods that optimize should converge, should be able to converge that optimum. In fact, if you want to explore the thing as a side credit, like not for the grades, you should take a data set where you can compute this exact, like spam base. So some chunk of spam base, right? Compute this with linear algebra, and this should be the absolute optimum W's that you can get. And then you run gradient descent or Newton's method to see how many iterations it takes to converge to here. That'll be an exercise that I think would be a good exercise for machine learning. This is part of the supervised learning algorithm, so it's not really our job to do them now. It's part of the 6140.
So what do you mean by that the batch is more robust? If the result doesn't change, stochastic is faster.
It's possible that some pushes point that way, some points point the other way. The W updates, right? Because this is an update. So if you don't do it as a batch, you do one this way, one that way, one this way, one that way. You know, you may go back and forth with a stochastic update. But if everybody pushes in direction, stochastic update is faster. Okay, so this is a regressor which doesn't really work for classification, right? It's suitable for when my Y that I want to predict is a quantity, like in here. It's the price of the house. So what do I do for classification? For the data set you have, I'm not sure you have spam base. Maybe you do. Not spam base. Housing data set? Do you have that one? Housing, I think the labels are prices. No.
Housing, we don't have labels. Housing, we don't have labels.
I'm confused then. There is another housing data set for which the housings are prices.
Yeah.
So we can add that to the homework if you guys want. It won't matter much if you run a library, because in a library, you don't control those things. I think that's a very useful exercise if you implement regression yourselves. And if you are data scientists, I would definitely, if I were you, I would implement regression by myself. And this is one of the basic exercises that you can do. If you implement it yourself, then it makes sense first to run it on a data set that Y is a quantity, like a price. Because you don't want to do logistic regression at first. But if you run a library, you just set the parameter, it's going to do the logistic regression for you. So how does that work? What we want to do with the logistic transformation let's call it G is 1 over 1 plus E and minus Z. How does that look if I have to plot it? When Z is minus infinity, what's the value of that function? Z is minus infinity, minus Z is plus infinity. E at plus infinity, infinity, 1 over infinity, 0. So that's 0 right here. That's going to start here at 0. Right? 0. And if Z is plus infinity, E at minus infinity is 0, 1 over 1 is 1. Right? So that's going to be, this is 1, 0. So how is that going to go? It's going to be like that. And when E is 0, E at 0 is
Half.
1. 1 plus 1 is 2, so that's a half. So in here it's a half. It's going to start from here. It's going to be rounded, going up, and end up 1. This is the logistic function. And how do I make it more stepwise? How do I make these round things? Like suppose I want to make it much more sharp. Sharp means there is a much more sharp transformation here, right? Or smooth. Smooth will be a much more soft. What would I need to do to make it more sharp or more smooth? I have to add something here, some sort of value, like a parameter. Let's call it, I don't know, beta. Beta times minus Z. So this is, when beta, let's call this beta equal 1, that's the default one, the logistic function. What do I have to do with beta to make it more sharp? Increase, this is beta equal 3, and to make it more soft, decrease, beta equals 0.3. If I want to play with how sharp this logistic is, the original idea of the logistic function comes from, I showed you last time, it's a step function, right? That cuts a threshold in the score, in the regression score, and says everybody more than that threshold does something, it's positive, and less than that it's negative. But we don't like sharp things, like very corner things in mathematics, so we came up with this smooth transformation. So what we're going to do, we're going to call h of x, that's our regression score. But we're not going to predict based on h of x. We're going to call g on top of it. G of h of x is our predictor. It's in fact interpreted as a probability of y equal 1. Y being the class I'm trying to predict, right? Because the more the score, the regression scores goes to plus infinity, g on top of that, g of this score, so this in here would be h of x. That's my z. The more it goes to plus infinity, the more g of h of x will be close to 1. And the more it's minus infinity, g of h of x will be close to minus 1. 0. That I'm going to interpret that as it's a fake probability. it's not really a probability in the natural sense. You know, what's the chance of a student in here getting a C- in this class? I can measure that by looking at the grades, right? And I can see what's the actual probability. This is a fake probability or a model probability. It's coming out of mathematical formula. And if a score is very low, I would say the probability of that class is becoming very close to zero. Right? That's the question? Yes.
Like what would we want a steep bar and a small school? Like, is it one?
So that has to do with confidence, you know, how much you want to have a probability. This area in here corresponds to probabilities that are big, but not that big. This area here also corresponds to probabilities that are interesting. If you want to reduce those areas, you know, if you are very confident in your threshold here, you may want to say everything that's below that threshold is absolutely confidently negative, everything positive. That corresponds to a very sharp cutoff. If you want to be like more like probabilistic, you know, I'm not sure, I got a score, a regression score here, my probability of being 0 is 0.4. So the probability of being 1 is 0.4. Sometimes we want to count probabilistically for the class we have. Like we don't want to say black or white. We want to say we think the probability of getting, I don't know, a grade or a color or a disease is 40% or 60% or 80%. Many models evaluate not based on black and white, evaluate based on the actual probabilities. So what happens is this sharpness control how much you want to account for that probability. With a very sharp model, all probabilities will be either 0 or 1. As soon as the regression score passes the threshold, immediately becomes 1. In a soft model, sometimes we want to account for scores that are close to the threshold, but not on the other side. That's the intuition. Okay, so how does this work? First of all, what is the derivative of this function? The regression, that's the whole thing here. The logistic function alone. Do we know how to differentiate that? I have a formula. You can tell me if it's correct. I don't know if it's correct. You guys can verify this.
Take the numerator and then different.
What?
You take the denominator to the numerator, it is easier to see that.
Right. This is without beta. This beta equal 1 in here. Yes.
This is for a black and white thing, right? So like two categories.
No. The beta was just a side conversation. I'm only going to use this beta equal 1. So I'm not going to make it square, like completely sharp. I'm not going to make it very soft. I'm going to use the default beta equal 1 logistic function.
So like how many categories would you say?
This is for a binary classification. It's either spam or no spam. If I have 7 categories, I'll have to have 7 logistic regressions.
Okay.
So I run all of them, and whoever gives me a higher probability, I'm gonna output that. So suppose I have car brands. I run one Toyota, not Toyota.
Okay.
Mercedes, not Mercedes.
Oh.
You know, Honda, not Honda. And then I run all predictors. Whichever one gives me the highest probability, I'm gonna predict that. That's a naive version. There's a better way to do it than that.
Okay.
There's a multinomial regression version. But again, you should take 6140. The basic idea here, if I have multiple classes, I run multiple regressors and take the biggest probability. Right? Okay. So assuming we understand this, how do we differentiate now this function? So what would be my objective now? My J becomes 1. So the objective for logistic regression, so let's do that here, logistic regression, has the objective being likelihood. That is the log likelihood. Logarithm of the product, so I equal 1n, of the probability of the correct this is my likelihood function. So this is going to be measured as product of G of H of X G of H of X at the power 1n I. Don't get scared because this is much simpler than it looks. So what happened here? Remember, the likelihood is a product of probabilities to see the correct label given the data and the parameter models. The parameters model for regression are the W's, right? So this probability is a fake probability because I'm actually computing with my own scoring function. I'm trying to model the reality with my regression function. So this is the probability that comes out from my regression, right? So this big pi is from I equal 1 to n. That's the probability over all the data points, just like before. What's the meaning of this times this? This is a very fancy and complicated way to say, is the y equal 1 or is the y equal 0? Out of these two factors, only one will count. For data points that have, this is a binary classification. For data points that have y equal 1, say spam, I'm going to count the p, the probability of seeing spam, right? So if the y is here, y equal 1, I'm counting how much the probability got to 1, right? So if the y equal 1, what do I want my g of h of x to be? Very high. Which means g is just the logistic function, which h of x should be very high, right? So we want this close to, if y equal 1, we want this close to 1, which means we want h of x close to infinity. If y is 1, this term doesn't matter, this factor, right? Because 1 minus it doesn't matter what's inside. It will be completely neglected. So you should really see this as a product over the data points that have y equal 1. It's this factor that matters. And the data points that have y equals 0 are the data points for which I want my probability to be very low. So in there, I'm going to say, take my probability and do 1 minus it, right? Because the probability, g of h of x is the probability of y equal 1. So who's the probability in my fake probability of y equals 0?
1 minus.
It's 1 minus g of h of x. So for the ones that are negative, the data points that are not sick or not spam, I'm going to make the product over 1 minus the probability. And I want those to be close to 1. So for y equals 0, we want this whole thing close to g of h close to to 0, which means h of x close to minus infinity. So what is this? This is a sum for all, because I'm taking the log of a product there, y equal 1 to n of yi log of g of h of x plus another sum one minus yi I'm just distributing the logarithm over the product. So now I'm going to skip this derivation, it's in the notes. If I differentiate this with respect to a w, I need to know the compound derivative. So how much is g of h of x differential with respect to x? How do one compute that? Do you remember? How do I differentiate a function applied on top of another function? Is the differential of the outer function differential first to h of x, right? And then multiplied with the differential of h of x with respect to, is that true? Some people in Europe don't write this notation with delta, they just say prime, g of h of x, that's the differential, is the differential of g applied to h times the differential of h. So I'm going to need that differential. I'm going to skip this in here because it's in the notes and you guys are going to follow from the notes. What I'm getting is y minus g of h of x times x k. If this is component k, x k. Which is very similar, if not identical, to the one that I've got here. In fact, if you think of this as the predictor, I miss a 2. My notes have a 1/2 in front of the objective, so they don't have a 2. Right? If I look at the objective and I put a 1/2 in front of it, I get rid of this 2. But that's small. It has no implications to the actual optimization. If you look at this function, that's the same as this one, with the only caveat that this is a regressor, and that's a logistic applied to a regressor. So what we're going to have here is the gradient descent update rule. Old. I've got the signs a little bit messed up, but plus yi minus g of h of x. So it's the same update rule that's written backwards. This is y minus, and it has a minus sign in the front. That's the regressor. Y minus the regressor with a plus in the front. Same update rule. And it's the same if you think of this as your all function. If you think of this as a function f, and if you think of this as a function f, which is the predictor, then it's the same update rule. So the complication here, again, is that we have this logistic function that also needs to be differentiated. It's a cascade of differentials that has to go down. But in the end, we optimize this. We optimize for the probabilities in here, probability model. And once we're done, we get the W's. It's still a convex objective. We get the W's in the optimal spot. We have our W's. We can call this on test classification. Now data points. How the test gonna go? I plug in the x, right? H of x will give me a score, just like in a regression. Then I apply g on top of it. G of h of x will take the score, whatever it is, will map it into a probability. And I'm going to say that's my probability for 1. If that's spam, that's my probability of spam. It's a sick people, that's probability of being sick. If it's the probability of being, the image is 2, that's probability of being 2. That's logistic regression.
So the beta becomes the hyperparameter.
Yeah, I think people can play with betas. They also have some prior that I don't have in the notes for what if I don't want my threshold to be at 0, right? I want the threshold to be somewhere else. How do I move that? It doesn't change the way the optimization goes. What makes this difficult is two things. One thing is regression, no matter how hard you try, it's going to produce a line. If the data doesn't fit a line, suppose I have some data that's like a curve like that, no regression function will fit that, right? So regression, this whole optimization thing in the end produces a line. So it has to exist a good line in there for me to find it. If there is no good line, regression will not give me. That's true for all models, right? If I'm looking for a particular model of a certain class, and there is no model in that class that fits my data, no matter what optimization method I'm using, I'm not going to find a good model. So that's one thing. The other thing is the objective that's optimized here. If I apply the same thing in machine learning, we have many different objectives. The moment this objective is not convex, optimization becomes much harder. So a lot of the EM problems are difficult because the EM objective is not convex. In fact, it's very bumpy. Makes it harder to find with numerical methods the optimum. Okay? Now, this is not a machine learning class. So if you really want to learn this, you should take a machine learning class because they spend 6 weeks on regression. And there is regularization of regression. Everybody knows how that works? Everybody? So how do I regularize? What regularize mean, first of all? I want the W's to have a certain property. So this is free W's. This is saying, give me the best W's, whatever. I put no condition on W's. Now suppose I want the W's to have, I prefer W's who have low L2 norm. In other words, I'm saying I don't want W's that are really big. This is the vector W, which is the sum of WK squared, right? So if I look at their squares, I say I don't like big squares in there. So that's one option for regularization. The other one is I want low L1 norm. So that's the sum of the absolute values of W. So why would anybody want such a thing? What's the effect on regressor? It's still optimizing the same objective. Tries to find the W, tries to minimize the error. If it's regression, it tries to do the square error loss. If it's classification, tries to do the likelihood loss. But why would I impose such a condition?
Isn't it 10 bigger than outliers?
So, right, what does that mean? What's an outlier in my plot here?
Because if it's not going to fit the line.
Very far away from the line, right? It's here. That's an outlier. The question for an outlier is how much an outlier has the power to drag this line with it. Regression is pretty good with outliers because it's a low complexity model. So one point alone cannot drag the line too much. Although you have to be careful with that square loss. This square loss, it's very big, may overcome the other square losses. The quadratic function, even though I have hundreds of points in here with small losses, one big loss may have an impact and may start dragging the line. That's not what I had in mind, but it's a good observation. Other models that are more complex models are more sensitive to outliers, like say boosting models. Regression is not so bad to outliers. In particular, it's quite good if I have outliers on both sides. If I have outliers on both sides, my regression will still be nailed down somewhere in the middle, so that's not bad. Algorithms that organize different places of the space in different ways, they have the tendency to do stuff specifically for outliers, and then that's a problem. What this does here, in common sense words, it's saying we don't want big squares, so if you can, spread the coefficients. So what I want you to think about it for this regularization is what happens if I have three features, F1, F2, F3, that are identical. Identical. So I'm taking my feature, which is blood pressure, and I'm putting it 3 times there. Now, any combination of coefficients here will have the same exact impact to the sum, right? Regression does a sum, and since those 3 attributes or columns in my data are identical, the regression might say, how about we give this one 100, 0, 0, or give 0, 100, 0, or give 40, 20, 40, or give 30, 40, 30. All those things will actually be the same exact function because it's sum of this times that, but those 3 are identical. So these combinations will produce the same result. Okay? So what is this? We don't like big squares. We don't like big squares is going to create combinations like this. Because 100 square, 0, 0, it's much bigger than 30 square, 40 square, 30 square. Right? Since those do the same thing for the objective and for the function, L2 regularization says if you can, spread the coefficients on correlated features. Of course, on non-correlated features doesn't make sense because it does not do the same thing. But in practice, if you have 780 dimensions or 100,000, many of them must be correlated. So L2 says spread the coefficients. It's a default regularization in all packages. We don't want big coefficients or arbitrary big W's. Arbitrary big have another problem. If I have an arbitrary big W, I get a test point that has a significant value for that column. It's going to jump instantly to plus infinity or minus infinity. Right? So this is a safe regularization. Control the size of the regressor, the W's. This one is more complicated. It says, I don't want many things that are non-zero. If you can, especially for text, I don't want you to spread the coefficients over really 100,000 columns. Just try to spread it over 1,000 columns or 2,000 columns. So L1, it's kind of reducing the complexity because if I really have 100,000 dimensions, the regression could be quite a complex classifier. It has 100,000 parameters. But L1 says don't use all of them because that's too complex. Use fewer than the maximum. Now again, we don't have time to get into that. How do you add regularization to the model in the math? You have to plug it into the objective somehow and include it in the differentials. So there is a way to do that. We can add some constraints here. We say plus something, differentiate, and get. You don't have to know how to do that for this class, but you should know when you call your package, what's the effect of L2 and what's the effect of L1. I'm sure the libraries that you're going to use allow you to use penalty or strength for regularization. The more strength you put, the more you enforce that property. Right? So if you put a lot of strength of L2, it will spread the coefficients as much as possible. If you put a lot of strength of L1, it will not give you too many coefficients that are significantly higher than 0. But this is good for feature selection. A strong L1 regularization, and then all the small coefficients, let's assume they are 0, even though they're not exactly 0. We take only the ones that are significantly higher than 0. We getting 2,000 features there. Now, So that's regression. I asked you to come here to give a demo, but before that, we didn't talk about neural networks yet. I'm going to give an intro. We're going to have to talk more about neural networks after the break, because neural networks are so complicated mathematically. We're going to use a different strategy than theory on the board, and then you go ahead and run it. I think neural networks are too hard for that. The ones of you, if you already see neural networks, that'll be a different story. But for neural networks, we're going to play with them first, and later we're going to see if we can understand the math, okay? So I think this works for regression because it's easy, right? But if I show you the math for neural networks, I'm just going to confuse you for no reason in the beginning. So how about we do the neural networks backwards? We first play with them, and then later we try to understand the math. So before we do that demo, I want to think of a regression in a slightly different way. I want to think with the graphical representation of my regression function. Here's what I want to think about. This is my input. So this is xi1, xi2 up to xid, right? These are the values of the data point. What happens in a graphical sense, they get added up, right? It's the sum of wi, wk, xk. That's my regressor, right? So I could imagine that the way that works in a graphical sense, there is a weight here, w1, w2, w3, up to wd. And what this operator does, takes w1 times this value, plus w2 times this value, plus w3 times this value, so on and so forth. It creates this, right? And then what happens here right after, next step, there is a logistic transformation. So this is a sum of branches. And then the next step is, take this, let's call this h, we call it h of x. I'm taking g of h of x. We're gonna know this, we're gonna draw right there the logistic function. Logistic, sometimes called softmax and nonlinear transformation, or other names for it. So this procedure here really is two steps, right? Do the sum of the branches, and then apply the logistic transformation on top of it, and that's the output. You can think of it as I'm outputting this, which is g of h of x, right? And then there's an evaluation node where it says, okay, subtract the label, do squares, or whatever. So the way you can think of this process is to say, if I plug in the x's here, assuming my weights are fixed, I'm getting a sum. I'm calling the logistic transformation top of it. I'm getting an output. Now, if the output is close to the label, I'm good, right? If the output is not close to the label, what does gradient descent do? Looks at this, takes the derivative, starts putting it backwards, right? Takes that derivative and say, how derivative? This is the second step. It applies here first, then here. And then eventually, what happens? Changes the weights. Gradient descent cannot change the input. That's the pixels or words counts or whatever I have in my data, but it can change this weights. It adjusts the weights. And it's already proven on the board that if I change the weights and I repipe it back, I get a smaller difference. This is conceptual because likelihoods work differently than this, right? So this is the objective. I want this to be closer to 1. I want it for all data points. This is drawing for one data point. So what does it mean for multiple data points? I plug in another data point, right? That's the stochastic mode. I plug another data point. I pipe it through. I look at the difference, take the gradients, back with the gradients, change the weights again. And I could pipe another data point now through, change the weights, and through, change the weights. And I keep doing it until the weights become stable. Like, okay, that's the best you can do for the sum. So we can call this the objective a sum here, or a product, because we want to minimize the sum over all the data points. But you can really think of one data point at a time. Go this way, it's a forward direction, right? And going backwards with derivatives and gradients is the backwards direction. How many people follow me here? Good. So you know what people have thought, nice. Let's complicate this thing. Right? How do we complicate it? Add more of these things, more square boxes to it. Okay? So they figured, okay, what if I add another square box here? Right? And then I have another set of weights to that box. That's a different G and H here, right? G maybe is the same. Let's say it's logistic, it's the same logistic function everywhere, but this is H2 of X. And this is really W1, 2, W, right? This is W2, 2, 2, 2. This is another set of weights that this one's over here, right? It's a different linear function. Called G of H of X, that's my output, right? And people have thought, we can keep going. We just not add multiple regressors. We can add now another entire layer that does the same, but now with the original input, but with these boxes. So what I'm going to add in here is another tool that says, okay, take this. This will be another. This is weight 3 that goes in here. And this is weight 4 and weight 4 that goes in here. And if I have multiple one of these ones in here, this will be also another weight 3. Those 3 weights will be the weights that goes in here. So these boxes are very similar, all of them. They all add up the weights times the output from the previous box. So they all do a little bit of sum of W3 times the output from layer 2, right? And then apply G on top of that, which is the logistic nonlinear function. It creates a new output. This one does the same. Sum of W4 times the output level from this layer and applying it to a logistic function. If I want, I can keep adding boxes here. This is called a neural network. And we're going to do the math later. Yes?
Could I ask, how do you initialize the weight in the beginning?
You will tell us how to do it. There's a lot of engineering going on. Your first exercise in homework 3B or 4, the next one, will be just install this and set it up. It's not that easy. Okay. So before Yu does the demo, I want to show you very, very toyish examples of something like this. Yu is going to show you something that's not toyish. So there are several implementations of neural networks. You're going to have to use a particular one of them, implemented by Google. It's called TensorFlow. So we're going to have to install it and run it. I don't have it installed on my computer. I'm running a demo version of TensorFlow, which is the actual TensorFlow, but very, very basic version. What Yu is going to show you, we actually install all packages and everything necessary to do TensorFlow. Some of you might have seen this. It's because it's quite popular. So this is the network that I was drawing on the board, right? So first of all, let's select a data set. This is a data set that's extremely easy to classify. X is 2-dimensional, and the labels are blue versus yellow. The inputs, if I really want the coordinates, I'm going to select here. The inputs are x1 and x2. Right? You can see they have a little picture that tells you this is the horizontal coordinate, that's the vertical coordinate. Right? And then this is my middle layer. All the layers are sum of the weights times the inputs, like I said on the board. On top of that, there's a logistic function, and then it's outputted. In here, I only have one layer, and the output is simply the likelihood function, right? I could add another layer if I want. So if I do this, I start doing gradient descent, right? After a few iterations, it's already converging. And the size of these lines corresponds to the how much weight they've got. So if a skinny one got no weight, a big one has a bigger weight. So what happens? This obviously this is a very easy data to classify in 2 dimensions. Suppose I even just want to do 1 dimension. I'm only taking the 1 coordinate of the data here. Even then, I can probably do it quite well, right? Even if I'm only using 1 coordinate, I can find the separation between yellow versus blue with 1 coordinate, right? What happens if I use this data set? This data set is much harder to classify based on that 1 coordinate alone, right? So let's try this. It's going to try the best it can based on only that coordinate. And it's going to do okay, but inevitably it's going to find some mistakes here because I give it an input, just the horizontal value, right? So I can stop this. And what happens if I add, for example, the sinus kind of function? Sinus is a periodic up and down function. It's a combination of x1 and x2, right? Sinus can be computed of those two. Let's try to run that. Apparently, sinus doesn't contribute much to this classification problem. You see how those weights are much bigger than those weights? The neural network figured out, I can use a little bit of this yellow one, but this one is very skinny. The weight is very small, right? And it doesn't do much of a better job. What if I add this one? So I have now 3 input coordinates, 3 input features. I have the x1, horizontal coordinate. I have the x2, the vertical coordinate, and I have the sinus function, right? So I have 3. I could run this. Because I give it more power, it finds something that's not exactly what I have in mind when I generated this data set, but it nevertheless matches, right? This is a much better loss than that. And again, I can look at the weights and say, okay, how everybody contributed. Bigger plots means bigger weights. What if I remove this one? It's the best you can find in those 2 things. So I can play with this. I can add another node here. Run it again. This one with more hidden, more intermediary nodes, it can kind of does better, right? But again, we can see the weights: small weight, big weight, so on and so forth. Or I can remove those.
The 4th neuron has no input.
What?
The 4th neuron has no input.
There is no output.
There is.
It's not visible.
That's like very low input.
Yeah, let me show you if I add more layers. Right, I'm adding these ones now, so I make this one bigger. I think this is limiting too much what happens in the network now. Let's make this one bigger. That's pretty good, right? How about we try a different data set? It's a different data set, right? For this data set that's so interleaved with each other, I may need a different input feature. It's trying to do something. It's not going to get it right, I don't think. Again, you can see which. Well, what if we add this? See how this got a big weight here? Because it's having a contribution to the data. Of course, the data cannot be matched based on these features here. What if we add more features? I add the squares and the product, right? Trying very hard. And you can see the loss function moving. This is the training and testing loss. It's not performance, it's how much that loss likelihood or something went down. So it's kind of have a hard time figuring out what to do. But you can see that it's trying. Right? So for now, we want to have this conceptual understanding of a neural network, which is more regressions, more logistic regressions on top of each other. Of course, the mathematics will have to be, how do I differentiate the output all the way back through all regressors, right? Because I not just have one, I have one layer, differential again, propagate the differentials all the way back, change all the weights in the network. We're going to deal with that later on. For now, I'm going to ask you to give you a demo on the real TensorFlow, not on this website. You have a HDMI?
Yeah.
HDMI? Camera a little bit.
So Virgil just explained conceptually how the neural network looks like in graphical way, and then this is basically how TensorFlow thinks about the architecture itself. So essentially, this placeholder is where you input all the X data into the TensorFlow, and then the model part is basically what Virgil describes as those black box. And here I'm going to show two layer. It's going to be a little bit nasty, but but conceptually it's two layer of black boxes. So here, the first layer is called hidden one, and I'm naming it as encoder. This is really just the weights for the first hidden black boxes. So essentially, if you look at this, the data inputs from here, where the placeholder provides the input X, and then it's multiplying. So here the white circles are all operators, the math operators, and these are the weights and the bias for the first hidden layer. So essentially your input X comes in, and then you multiply with your weight, and then you add your bias. That's essentially correspond to the math part. And then you add a sigmoid, which is the fx, wx plus b. And then this goes to the second hidden black box, which here I'm naming it as decoder hidden H2, which is the weight for the second layer of black box. So the output of the first black box layer goes to as input for the second layer of black box, where you times your weight and then plus your bias. And then this goes to the output of the whole model module. That's how basically TensorFlow thinks about the model itself.
So it's nice that it comes with this visualizer. This tensor board is a way to see the network you've created and maybe to analyze it. You have to log everything to be able to do so.
So yeah, so once you have the output from the black boxes, then you basically construct a loss function. That's basically the difference between the prediction and the actual ground truth, where you subtract the output from the model, and then the placeholder again is where the actual input comes in. This is your y truth. You subtract them, and then you take the L2 loss, and then this goes to the optimizer, where that's when you backpropagate all the loss back to the neural network and update the weights. Does it make sense? Right, so this is essentially the same thing, but in code, and this is the output. So the placeholder will take in this input data, which again is in matrix form. TensorFlow essentially is the same as NumPy. The whole data structure follows the same. So it's all matrix. So for example, here I'm taking in 8 data points. Each has 8 dimensions. And then this is the output of the first black box output. And then first layer of black box. And then this is the output for the second layer black box. You can see, so a little bit thing here is, this is essentially an autoencoder, which your output is same as your input. So you're supposed to reconstruct your input and then to find a compact representation for the input data. So in this example, the input is 8 number, and then you can see after running the whole algorithm, it's able to find a representation for each of these data points in only 3 dimensions. And then the reconstruction error is pretty low. So now I'm going to explain a little bit how the code
So
looks.
hold on, this is something I didn't say, run out of time. Give me 1 minute. I'm gonna, you can keep the laptop there. What you're saying is that you're gonna have in homework 4 2 exercises with TensorFlow. Really quick, I'm gonna do a drawing here on the board. So I have my network, right? This is the input, xi, and I have designed a middle layer. We call this hidden layer. And I can have multiple hidden layers, but for now, let's just say we have one. And then I have an output here, right? We say for classification, this is gonna be how close is the predictor to the error, right? So for classification, I have a output minus y metric, right? Say sum of or evaluation of. That one minimize. What you're saying, we're gonna use TensorFlow in a different way. So that will be an exercise in homework 4. That's just supervised classification. We're not gonna do classification. What we're gonna do, we're gonna put the input layer again in here. So I don't have labels this time. There's no y. I'm storing the x1, x2, x3, xd again. And I have a full set of weights here between those. What's the purpose of doing this? Why would I do such a thing? She calls an autoencoder. If my output matches exactly the input here, this is still effectively output minus x1, output minus x2, right? Evaluate. You want the output to be exactly the input. What did I achieve? The hidden layers, it's a dimensionality reduction, right? Maybe there are 784 things, and I represent on 20 things. If I get the output to be the input, it means somehow it passed through 20. I can represent every image with exactly 20 values. Which 20 values? I plug the image here. Whatever values I get in here, that's my new representation. So I achieve a dimensionality reduction from 784 to 20 dimensions. So you guys are gonna have this, once you set up TensorFlow, you're gonna have to run both exercises. And that's what she's done here. she has an autoencoder set up.
Yeah, so essentially this TensorFlow has a very flexible structure that can achieve both unsupervised learning tasks like this autoencoder or the classification task of predicting the label. And then the whole difference is that when you set up the architecture, you just have like, from the graphical structure side, you have one node versus like all the other node, where the other node here as autoencoder represent the whole input X again. Let's say if you have a classification task, then your output node would only have output layer, the second hidden layer would only have one node. So programming wise, it's very similar. So here I'm going to show you how the program looks like. So,
one more thing, TensorFlow, it's an optimization routine written in C, but to set it up, you set it up in Python.
right, so yeah, I'm going to show you a little bit how to set it up. So again, like the full thing will be, you can find it on the official website. It has a very, very comprehensive guideline about how to install it. But then here is just a snippet of me give an example how to set it on Mac using Python 2.7. So essentially, you started with setting up this virtual environment. If you use Python, you know that Python has a lot of package conflicting issue. So this is like a nice safe container to avoid that. And there's other options, but virtual environment usually is the most lightweight one that I would recommend. So once you have that set up, then since we're not going to use a GPU version for this, everyone should be able to just install an easy CPU version on your computer, and it's really just two command line. And then once you do the install, then you can just easily test it by going to your Python command window and then just do import TensorFlow STF and print out the version number, and then do a quick session. I'll explain what session means. And then if you can run the session and then print out some message, then you're basically all set. And it's actually pretty straightforward. It's just three steps. If you need you probably need the debug. If you do need help, just come to office hour. So once you have the Python set up, obviously you can just next step is to get your Jupyter notebook or any Python editor. So here I'm using Jupyter. So here you first want to define all the components. I described it before as like the input placeholder, where you just call a placeholder. This is a Python object in TensorFlow. Then you define your model part, basically setting up or describe the model. This is all the things you would need, the chunk of code that you describe it. Essentially, it's the same as describing the math, the operators, and then just that's all. It's essentially the same as this. And then once you have the model described, then you have to set up a loss function, loss module, where again it's describing what the loss would look like. And then finally, you describe your optimizer module. So up till here, you would have all your graph described. Now, how do you run it? So that's when the session comes into play. Session is basically when you start to interact with the graph by inputting the data and then see how it runs. So once you have the session set up, then you can basically call session run, and then which you run your output node, and then you have to feed into this graph your data, which here is called it's basically using a feed dictionary thing here. So once you get the session running, then you should be able to just print out the results, and that's basically it. It's two steps: describe the graph and then run the graph using the input data. Does it make sense? So should I give a? So I'm gonna give a demo on the MNIST, and then let you feel how it runs.
Autoencoder?
Yeah, for autoencoder, and then close this. So it's gonna take about 5 minutes to run. Yeah, for during this time, do you guys have any questions?
Did you start it?
Yes, it started. It's just gonna take
So
some.
to be clear, we expect that you guys gonna need a lot of babysitting on TensorFlow as compared to say regression. Like I don't expect you're gonna have any difficulty running linear or package decision trees, but we do expect that a lot of people will come to office hours and say, okay, I don't know how to set this up, help me. I don't know how to define a loss. I don't know how to design the network. That's okay. We assume you didn't do neural networks before. But this week it's busy with the other homework, the 3A, the PCA homework. So I would like you guys to try to install it, at least TensorFlow and Jupyter and Python and everything else that's required over the break. So when you come after the break, we don't deal with, okay, you don't even have TensorFlow on your computer, so there's nothing to set up. Right? So this part, I would like you to try to install the required packages. There'll be an installation. You wrote an installation note. What are the steps that I need to be doing? Maybe she cannot verify this on a Linux or Windows computer because she has a Mac. So if you have I expect Unix to be the same as a Mac, but on Windows, if anybody has a Windows computer, we're going to deal with that. Okay.
So yeah, just since we're waiting, so this is like basically how you set up one layer. It's just very easy, where you multiply your weights with x, and then plus like TF add is essentially just adding the bias, and then you call the sigmoid. That's just how convenient this whole thing is. And then if you have two layers, essentially you just for your first layer your input is x, then the second layer your input is the output of the first layer, layer 1. And of course decoder is essentially the other side, which is a mirror of the first side. So for MNIST, I'm using for the first, so here for MNIST there's another layer here and then another layer here, and for this layer I'm using 255 nodes in this layer, and then in the middle layer is 128 nodes. I'll point you guys a little bit to reference online. There's a lot of resource online that has already a lot of examples for you that you can refer to. So it should be pretty straightforward. There's a lot of people doing the same thing here. So I'm running about 30K steps. On my computer, it took about around 5 minutes. Any questions?
So what if you have a GPU version already installed?
Sorry?
If you have a GPU version of TensorFlow already installed, it's fine, right? Or-
Yeah, that'll be even faster. Like
It's harder though to set up the GPU version. So I'm not sure how much help we can provide for that. That'll be better for you if you, TensorFlow being a neural network is designed to run on CPU or GPU. So GPUs it's faster. If you can do on GPU, that's better. But it may be harder to do the setup, right?
In general, most laptop doesn't have the NVIDIA GPU setup, so it's really hard to get it running. But if you have access to any clusters, that'll be great. It'll be much faster than this. So this is like, I think my computer is a little bit compared to average, is on the powerful side. So if you have any trouble like running it, the suggestion is to always reduce number of steps. The good thing about running TensorFlow is that it runs on a minute batch, in the sense that you don't have to feed the whole thing into the pipeline once. You don't have to feed out all the data points once. You can take, let's say, 100 data points once, and then it will keep updating. So if you're feeling that computational, there's a lot of computational burden on your computer, you can try debug it by reducing the number of steps you run, and then see how the result looks like. So I'm giving you an example that after 30K steps, each step you input a minute batch of 56 data points. You should be able to achieve very, very good results for the reconstruction and autoencoder task.
Did it run?
Yeah, it has another 10K steps. anyone has more questions?
So I think the GPU version uses CUDA, which means you need an NVIDIA card.
I already installed for the previous project. I don't know whether it's working or not.
Oh, so there's a command that you can just print out the device you're using. So usually it will tell if you're running on CPU or GPU.
So if you have a workstation computer at home that happen to have an NVIDIA graphics card for playing games, that's a great opportunity to make actual use of that card. But if you have a laptop, you probably don't want to buy another laptop just because you don't have an NVIDIA card in it.
Almost there.
Almost.
So there's another 5K. So it's like 5 iterations. 5 print out.
So as an autoencoder, we're going to do something similar with the current homework. We take those features that are the 20 features or 30 features from those images, and we repeat some classification tasks or clustering tasks with them, just to see how it they do.
How would this be when running on a cluster?
How would it run on a cluster?
You mean distributed TensorFlow?
Yeah.
I think there is a version of it that's in parallel.
Yeah, I mean, TensorFlow, basically, if you set up in GPU, it automatically, you can just program into the distributed version. But syntax-wise, it requires a lot of things. Like you have to, let's say, microcontrol, like, which operations goes to which GPU. It's not very straightforward.
Yeah.
Right, so.
So how do you know these features are good?
Oh, I tested on the k-means.
I see.
Yeah, and some of them does make sense, some doesn't. Right, so 7 minutes, and then this is so this is basically the output of the reconstructed image.
So that's cool. What you did here, we have 3 minutes and we have to go. What she did, apart from rerunning a classification or clustering task, she looked at this output. She looked at this reconstructed image. She plugged in a MNIST image here. The network is run now, it's done. Middle layer, computing the new 784 predicted pixels. And instead of comparing with the other pixels or use those, the middle ones to do clustering, she said, okay, how does it actually look as an image? I'm going to look at it with my eyes. It's the 784, not the true pixels, but the predicted pixels, right?
Yeah. So it's actually, you can see, like the first image is original image. This is like when you started your network. It's completely random noise. But then, like, after over the steps, it just gets better and better. And then the last reconstructed image looks very similar to the original one. It can't be like 100% reconstructed. There is some noise. So just to show you, this is a few examples. Yeah, that's it.
So I think for images, you can do this, you can see the images, but for other data sets like spam-based or text, you cannot do it because the reconstructed would make any sense. Thank you, Yu. We're gonna need more demos on TensorFlow, I think.